This is 1.8 notes. Up until this point, we've talked a lot about measurement in terms of how we know how accurate or precise our numbers are. And today we're going to talk more about what units we use to measure in a lab setting and how we make sure that those numbers are accurate. So why is it important to standardize measurement? Well, let's suppose you're in a hospital and the doctor asks you to bring one propofol syringe. That seems like a pretty simple task, but that could mean a lot of different things. Syringes are not standardized, they're not all the same size. So it's important that we use language and terms and types of measurement, okay, 200 milligrams, so that we're all positive on what is being asked of us or what was done in a laboratory or even a medical setting. So the system we use in all science is called the SI system, or the International System of Units. It is metric based. It's what you would think of as metric in the United States. Sometimes we don't like using this. We use our own system a lot. But this is what the world has basically agreed to use in science. So there's 7 base units, and those base units are used to measure all things, and we can use them to derive other units. So time is in seconds, length is in meters, mass is in kilograms, and amount of a substance, which is a mole, which we'll be dealing a lot with this year, we just haven't yet. Temperature is actually in Kelvin, current and luminous intensity, which we would be dealt with in a physics lab, but not in chemistry class. So within that system, we can use prefixes in front of words like seconds or meters or kilograms. A kilo is one of those actually prefixes to manipulate the scale of those measurements. So typically the base measurements that we spend most time on would be grams, meters, and liters. And then we could add like deca, hecto, kilo, mega, giga to those numbers to make a larger unit of measure. Or we could use deci, centi, milli, micro, and nano to make a smaller unit of measure. Notice the nice thing about the metric system is every time you add or you go kind of one click up on that scale, you're literally just adding a power of 10. So those terms, those prefixes which you're familiar with, especially the higher end because of the data that we use, we know like what gigabytes are, we know what megabytes are. A document, like a Word document, would be like a kilobyte, okay, or multiple kilobytes, depending on what's in it. And you know what a millimeter is or a centimeter is. So you can kind of see where you are on that scale, and it helps you use them appropriately. For instance, if I asked you how far you lived from school, you wouldn't tell me that measurement in millimeters. You'd have a giant number, and it'd be like really difficult to deal with. So what would we do? We'd probably measure it in kilometers, depending on how far you live from the house, because it's a larger unit of measure that fits the larger distance. There are other prefixes that go all the way out to times 10 to the 24th and farther. We just aren't going to deal with those. The ones on this sheet right here are the ones you're responsible for. And you don't even have to memorize them. You'll have this number line that's on your equation sheet. The base unit's in the middle, and then as you move left, you have deca, hecta, kilo, and then the dots are just placeholders for times 10. You would not need to know the prefixes for those, but then you would know if you went 1, 2, 3 to the left past kilo, you'd get to mega, and 1, 2, 3 to the left past giga, or mega, you'd get giga, and so on. So we'll use this here in a couple seconds. Before we do, just to give you an idea, we are starting to get to terabytes. Like if you have a computer at home, you probably have a terabyte hard drive at this point in time, maybe if it's a newer computer. We're starting to store things in the cloud, so that changes. But petabytes would be the next place to go after a terabyte. A petabyte could hold 13.3 years of HD video. And 1.5 petabytes is the size of 10 billion Facebook photos. And then at the bottom, I think this is interesting, 20 petabytes is the amount of data processed by Google per day. So that means, like if you took 20 and multiplied by 13.3, that's how much HD TV video that Google would be processing every day. That's insane amounts of information. So you might not think in terms of petabytes in terms of your local home computer, but there are companies that do because of how much information they process. All right, let's do some example problems on how to convert from a larger unit to a smaller unit using our number line. So for instance, we have 2.5 meters and it's asking us to convert to millimeters. So what we're going to do is we're first going to identify where we are. Anytime you just have a unit by itself, that means you're at the base. We are here at base units. And we're going to millimeters, which is here. 1, 2, 3. So we moved 3 powers of 10 to the right, which means to convert this, all we have to do is move the decimal 3 powers of 10 to the right, making this 2,500 millimeters. This is very simple. Wherever you go on the number line, do the same thing with the decimal point. On this next one, we have centimeters. Centimeters is right here. And we want to go to angstroms. 1, 2, 3, 4, 5, 6, 7, 8 to the right. So that means we need to start right here and go 8 to the right, which means it'd be 2, 4, and then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then you can put your commas in where they go every 3. Okay? So move the decimal on the number line, then move it correctly on the answer. I will say this though, sig figs matter here. This number here had 2 sig figs and we ended with 2 sig figs. This number here had 3 sig figs and we need to end with 3 sig figs, which means we need to put a line over this 0 to show that those 3 are significant. Next one, this one we're moving left. We're starting at deciliters, which is this D here. This is deca. And we're going to kiloliters. 1, 2, 3, 4 to the left. Meaning our decimal that's here, we're going to move it 1, 2, 3, 4 to the left. 0.00, there's going to be 2 zeros here that are placeholders. 13 kiloliters. All right. This next one is going from kilometers to meters. So 1, 2, 3, because meters is a base unit. 1, 2, 3. So this would be 400 meters. Notice there are 2 sig figs here. So 1, 2, there would need to be a line here because we need to show that that middle 0 is significant without showing the last 0 is significant. You can work on those last 2, but really this is just a straightforward process of figuring out which prefix you're starting at, which prefix you're converting to, and moving the decimal accordingly. The last thing we want to talk about today is how to calculate error. We have absolute error and percent error. Absolute error is basically how far away are you. It's the numerical distance. So if I said if you estimated how far you are from here, you live from school and you said 1 mile, but it was really 1.5 miles, your absolute error is 0.5. It's half a mile because that's how far off you were. But that can only tell us so much. So for instance, if I said you were off by 3 inches, that doesn't sound too bad if you're measuring the distance from here to your house. But if you were off by 3 inches when measuring a pencil, that's pretty bad. All right, that's a lot of error. So absolute error can be helpful, but percent error puts it in perspective. How much error is that based on what we're measuring? So the way we do that is we take the absolute error, which is EA, and we divide by the accepted value, or the known value, and times it by 100. And that will tell us what percentage, or how far off we are, based on the accepted measurement. So let's do an example here. You measure the density of a metal several times and find the average is 7.65. So you really need to identify these variables correctly. This is the observed error, or sorry, this is the observed value. Okay, this is what you observed in lab. And then the accepted value is down here at 7.15. So the first thing we're going to do is calculate the accepted value. And we're going to do the absolute value and we're going to subtract these two numbers because we want to know how far away we are. So if we do this, we would be off by 0.5. That is our absolute error, and it would be 0.5. It'd actually be 0.50. Why? These numbers both have 2 digits to the right. So that means our answers both need to have 2 digits to the right. So then to find the relative error, we'd take our absolute error and we'd put it over the accepted value, which is the 7.15, and we'd multiply by 100. So the relative error would be 6.993%. And I would say we should keep 2 sig figs because the 0.50 had 2 sig figs. So this would become, so the 2 sig figs are the 6 to 9, the 9 rounds this up, and the relative error becomes 7.0%. Notice that as I'm doing this, the math, I'm sure you can handle the math. It's knowing how to round and basically paying attention to your sig figs at all steps. That's really all we wanted to accomplish today. You should know how to convert different types of metric prefixes from one prefix to another, and you should also be able to calculate error at this point. Do the practice problems. Let me know if you have any questions. Good job. We will see you next time.